Okay.
Hello, hello, yes. A very good morning, everyone. I welcome all of you to the fifth day of our workshop. So, without any delays, let's commence our session for today. So, our first speaker is Dr. Claire Cannet, who is joining us directly from Ettlingen, Germany. I'll give a little introduction about her. Dr. Claire Cannet has done her master's in analytical chemistry and her PhD on inborn error of metabolism. She's currently working as clinical market manager at Bruker Biospin, Germany. She has been working with Bruker for more than 10 years, so she's none other than but an expert who will give us important insight in the field of NMR. So now I request Dr. Cannet to address the audience. Hello. Hello. Ma'am, can you hear us?
Yeah, you can start. Okay. Hello, everyone. I'm not seeing anything, that's why I was not sure if I can start. But thanks for the introduction, and I will have now this 1 hour. I will try to be on time, maybe just 45 minutes, to let them time for question, if any. But if you do not have now a question, you can just send me an email afterwards. This is really not a problem at all. Now I hope that you can hear me then properly. Yes. And okay, that's perfect. And today I would like really to give you a short overview about what NMR can be or can be used in clinical research and translation. And I will really then focus on one product line, Bruker Biospin has. And this is then the Advanced IVDR system, or the Advanced IVDR platform. And here I just put them two short pictures. And the one is just for illustrating them our demo lab in Germany. It is a special demo lab because we are dealing with human body fluids, and then it's really then strict or access restricted. And you can see here, I hope you can see that here we have then a 3 IVDR system, which is then working routinely, measuring the cohorts of urine samples, plasma samples, and CSF samples. And then, unfortunately, we cannot see that we have 3 other systems which are used for a more dedicated application, like structure investigation for unknown metabolites. And then we are using then, of course, then the NMR and the mass spec system in order then to find out any unknown compound in the body fluids. And then on the bottom left, it's just an operator which is then at the moment then using or preparing the sample for the measurement. This can be done manually, just pipetting, or you can use fully automated sample roboter, which is preparing sample for us. Okay, then let's start. And at Bruker, we have, as you know, we have mass spec technology and NMR technology. Today I will really focus on the NMR part, because I am an expert on that. And then what we, in the metabolomics field, what we aim is really then to work and to help customer in precision medicine and in molecular phenomics. And these mean that improve disease prevention, diagnostic, treatment, and now with the pandemic, for example, we have focused one application on the long COVID module. I mean that what are we doing then in metabolomics with NMR is we then try to analyze all the interaction between the genes, environment, diet, lifestyle. And this, the aim is really then to measure the longitudinal samples in order really then to be able to say something on the epidemiology level and focus on the health status improvement. As you all know, the population is, the age of the population is always increasing, which is really great. But mean that you are then increasing the health costs, and then we need to have some disease prevention instead of detecting and trying to correct some cancer, for example. And it's now really then since 10 years, it's really then exactly coming on the fact that we need personalized medicine and not one treatment is correct for everyone. And this is really then where NMR and the standardizing message could really then help. And of course, nutrition is an important part, and lifestyle, environment, the same. In this system, there is some groups which are called International Phenome Centers Network. In that it takes a center all over the world, having NMR system, using then the SOPs for standardization from Boca, and having then mass spec, mass spectroscopy technology, and measuring the body fluids in order then to make epidemiological study. And these groups are the founder and the lead from this initiative is German person from AAPC. And we are working then, of course, closely with the group and with all the other partners all over the world. And this is just some example about the different places in UK, in Singapore, of course in AAPC, but in London too, where you will find exactly the same system. And the beauty is that because it is standardized, you will then get, independent on where you are measuring, you will get the same results. And this is the idea is really that to share the data in order to obtain more information and then coming then with quick answer on different questions. And here is just the mission of this International Phenome Center is really working with standardized SOPs in order to exchange data to make common research. And this is working really well. And now with the COVID pandemic, it really shows the power. And then maybe you have already seen that there is a lot of publication on COVID, on long COVID, coming from this group, from this network, and this is really because they could share data. Now I would like to focus on exactly the system that we developed in order to have this standardization, and this is what we call the Luca IDEA NMR platform. And this platform is standardized, working in full automation, that you do not need to be an NMR expert to use the NMR system. This is really then something which was for us important, and it provides a research solution for metabolic profiling perspective, which can be then personalized or on a population base, like epidemiology. And then we can use this platform in different research areas, which can be then well-being, pharma, biobank, or within and for clinical application, like obesity, like pediatric, like cancer, and so on. And I will now say some word about the platform in general, and then give you then some example on different application. Sorry about the background noise, but in Germany it's really early, and I have my two daughters still listening. Yeah. Okay, that's we have these incubators. So give me just 30 seconds. Yeah. Sorry about that. Okay, in it, the IVTR platform is an integrated solution for really working on with human body fluid samples. And what we have is we have done the systems, and we developed then some modules on it to be used from any customer. We have we are speaking about different layers, and the first layer is about the NMR system. This is a 600 MHz system, which it is a NAMOS 3HD or NAMOS Neo with a sample jet, with dedicated probe head, and so on. And in order then to make the standardization, we have on top spin the modules, which is really done for standardization of the body fluids analysis. And it has a quality control step for checking if the system is working properly, knowing that we would like that non-NMR experts are using that. And then once you are using that, you can then use the different modules, Ruka as remote, and I will then go into details about the different modules. So, sorry, I don't know if it's working. I just then click on something. Can you still hear me?
Yeah, we can hear you.
Yeah. Oh, okay. Sorry about that. I will just restart here. We have the ICGEB-DBT platform. That it is really then a dedicated NMR system. It's a 600 with then defined configuration, and on top we have then standardization, which is then software, and it enables customer to with body fluid samples to get high quality NMR spectra. And with that, it is possible to make your own analysis, or it is possible to use the tools which Bruker has developed or other customer has developed and are available on the platform, and it allows you to get more information about the NMR spectrum. Meaning that you will get that directly sample parameters. This could be then concentration, this could be then lipoprotein parameters. And then you can then use that for statistical analysis. And we have some tools or some interface in order that to help people in different areas to help to interpret the research. And this is then, for example, one interface for the inborn errors of metabolism, which help to filter the result from the NMR and try then to find if there is any inborn errors of metabolism in this patient. Okay, this concept and this platform is already existing since 10 years, and we have already installed all over the world about 65 systems. And this is just some name where systems are already installed and used. And we are offering these modules to make, for example, quality control in biobank, lipoprotein in plasma serum, small molecules quantification in plasma, or small molecules quantification in urine. And this is something which it is not a software you get. In that it is that the algorithm are IP protected at Bruker, and that there is a lot of work done. And then it is working or via a cloud-based solution. And that the spectra are sent into the cloud, and the cloud it is some computers, and then they are doing the analysis automatically, and then when it is finished, it's come back to the spectrometer at customer site. And just to give you then some idea that every 2 minutes, someone is asking for a request, for an analysis request. Could be the quality control for biobank, could be lipoprotein, or could be done quantification in urine. But yeah. And since now 2017, we have already analyzed, or the clouds already analyzed more than 1.5 million analyses. It's really well used, more on the plasma application, but the urine is about 40% of the time. And just looking now at the usage of this platform and this tool, it is then easy to check on the publications. And here we have done more than 100 publications referring to the ICGEB platform or using the ICGEB platform and the different analysis tools. And in 2021, for example, last year we had done about 45 publications with a big part on the COVID research. Now, looking at the platform, what exactly then it is including. Well, like I said, we are analyzing body fluid samples, meaning that it could be then CSF, cerebral fluid, it could be the urine sample, it could be blood samples, it could be the saliva, feces. You can then analyze all the human body fluids, it needs to be done liquid. For biopsy, it is possible to do that with alongside 2, but you need a special probe head in order to do then the HRMRS. And this is something which I will not speak today, because this is something needs some expertise to prepare the samples. It's not easy, and to have the NMR, it is not at the moment working in full automation. But just to let you know that it is existing, if you want to have more information, I can then provide you with a lot of slides about HRMRS. For the liquids, it's really a body fluids samples, which is normally collected outside the NMR facility, and then what it is needed to be done is really that to store immediately the samples for the UV, for example, and then immediately then after always measure it or freeze them at -80 degrees. And then with the ICGEB-DBT system, we can then prepare the samples, measure the samples, and do the data analysis. And in average, it's taken 20 minutes per sample from the sample preparation to the data analysis. And at the end, you obtain an NMR spectra, but you obtain some analysis reports directly done from your NMR spectra. And why we are doing that is really important, is to get always the same results when you are analyzing the same samples. Mean that the standardization, automation, scalability, and sustainability are where the key doing the development. And here is just to plot here, one on the urine side and also on the plasma, and this is samples prepared, for example, on the urine one, 50 replicates from the same samples prepared from 2 different people, 2 different spectrometers. And then you see on overlay the 50 spectra, and you can see, even you cannot really then say what is then the signals maybe, but you can then see that it is exactly then the same from an NMR view. And the same is on the plasma. It's 50 replicates with one spectrometer, and here you see exactly the same. The peak are aligned. It's look always the same. Visually, I cannot see any differences. Here it is really that all the 50 replicate together, and here the same. This is then the creatinine and creatine, which is then really then important in a lot of study. And on the plasma, we have then the alanine and lactic acids, which are important markers. And this is again the overlay of 15 replicates, and you cannot really then see any differences. With this standardization, it is possible to do target analysis, and on the same spectrum, you can then do non-target analysis, mean that's statistical. And here is just an example, mean that you can have a healthy cohort, and then you can then have another samples you want to compare with, and then you can do that visually or with statistics methods. And now for disease marker, biomarker, you can then use then two different strategies. You can then run a spectrum and do a full, using the full automation quantification. But with the same spectrum, you can then really do a semi-automatic identification using the biomarker, so that's pure compound. And then you can then identify semi-automatically then more than 250 inbornials of metabolism, biomarker, for example. Saying that all is working with the semi-automatic quantification or identification. This is used with the Drucker software, which is called an AIMS. It is an Mitchell's analysis software. And on this software, we develop what we call a database of body fluids reference compounds. This is pure NMR spectra from metabolites or drugs or food ingredients which could be found in the body fluids. And then all the time it's a measure in full automation. And you can then get the standard proton NMR, resolved, but then you have then these standard 2D experiments like COSI, TOXI, HSBC, or HNBC. And then you can then directly then compare these spectra from the biorecord with the spectra of interest. And here it's just two examples. One is just the real spectra of the urine of inbornials of metabolism disease. And then you have then the different carnitines and pure compounds, and then it is then easy then to detect or to identify which metabolites are in the urine. And the same for the protein. On the complete solution, we have done for plasma samples. We have done different modules, like I already mentioned, and this is just a workflow. It's always working in the same way. You have the sample preparation, you have the measurement, and you have then the automatic spectra processing. And then with that, you can use the FTP and this service cloud based service, and then you can then do a quality control of each samples. You can ask for a lipoprotein subclasses analysis, or you can ask for metabolite quantification. And at the end, it's using a different algorithm, but then you can get a report with the different calculators. And this year, of course, we are always expanding our portfolio and modules. And this year we will add some inflammation biomarker inflammation. And this will be exactly working in the same way. You will then be able to ask for that on the cloud service. For the urine, the same, meaning that you have an easy sample preparation. It's just addition of buffer. You do not need to make any standardization, any extraction. And so on, that it is just pipeting the body fluids and adding some buffer in order to stabilize the pH. The same for the plasma. And then you have done the NMR acquisition, then the processing, and then you can then have the information about the metabolite quantification. or the end on the same data, the quality control. That at the end you get the spectra and you get the report where you get a lot of information about the parameters and the concentration, the LODs, and so on. And now, just thinking about the standardization that I'm speaking since the beginning, and this is just illustration to show you then this long-term reproducibility, that this is now a retrospective analysis of spectra from 2019 to October last year, in that it is about more than 350 quality control samples we have measured. And you can see that, of course, we change spectrometer, we change operators, and now what you can see here is an overlay of 300 or more than 350 samples. And you cannot see really a big difference in it. There is some variation, and this is clear, but this is really done over than 3-4 years. It is really done incredible. And this is done on the peak. We can see this is really done biomarkers. And then you have then, of course, the different lipoprotein and subclasses information which are in the different CH3 from the different lipoprotein, and with a regression model it is then easy then to get the information about cholesterol, triglyceride, and all the lipoprotein subclasses of them. Because this is just showing you, and we say for this slide, that when you are using the IVDR system and following the SOPs, you can really then compare the data over the years and over the instrument. And this is something which is really then helpful for the research on human health. Just to summarize, it is a complete standardization. You get really high quality NMR spectra. What you can do is you can then make what you want with. You can use then the different tools. It is really done, the sample preparation is really easy and fast. No extraction, no separation, just an additional buffer with pipetting. Then NMR is the definition quantitative, and we are calibrating the system and checking the quality control system, the quality control of the system every day if you want to do that, and then it is really an accurate and precise quantification. You have already done one excellent standard. You do not need to make any calibration code. You can then get with just one measurement the quantification of at the moment 150 metabolites in human samples. For the plasma, it's 40 metabolites and 115 lipoproteins. And I could show you that it is really reproducible and it is possible to exchange data all over the world. And that's good. With that, there is a lot of application. And I will not be able to explain you or to give you example on all application, but I just selected some in the cardiovascular disease, biobanks, nutrition, COVID research, and IM. And now I would like to go and show you that some example. And now, just starting with the nutrition aspect and well-being, this this is now all the example I can show you. It's really that done with this NMR system and this standardization. Why it is important in nutrition? That, and this is exactly what I said at the beginning, that it is important, or it has been shown that it is not working to say everyone should have the same diet, should make the same sport, and then everything is fine. That these need really to be personalized, and a lot of research are done, because then we are all different, and then with the diet and with the lifestyle, the metabolism of each individual looks then different. And there is then different application, and then it is really then one would be to. You want to say something? Or I can move. Then using then the urine spectra, you can then identify a lot of metabolites which are reflecting or giving you some information about the nutrition aspect or the food intake. And this is just an example that you have then the citric acid, you have then the cysteine, sulfoxide, this is really the vegetables, then you have the carnitine, which is then meats, then you have then the TMAO, which is then consumption of fish, then you have then a lot of other metabolites like tartaric acid for foods, and so on, or then microbiota metabolites. And these can be then used in order to calculate the impact of the diet on the personalized metabolome. And this is now a group of well-known scientific which are from Imperial College, who developed a solution. This is working then with our SOPs, and this is giving them a lot of or checking a lot of health-related parameters with one measurement, and then it's allowing you really to make a personalized assessment on the person, and then with this response, then consumer could really then change lifestyle, change diets, or make more sports, and then see where he can do effects. What's good is that for nutrition, then it is not static, in that you can, if you change your lifestyle, your metabolic profile will change. In that you can then change, and then you will then see then directly the change on your metabolism. And this is just some pictures about the different results you can then get. One side, it is then possible to compare your profile with the WHO guideline, the Worldwide Institution for Health, saying that you need to eat then 5 vegetables, 5 times vegetables or fruits in a day, and the proportion which will be then a individual diet. And this is just then comparing your profile to this guideline, and then you can then see the concentration of the different relevant diet metabolites. And here is just a profile of 2 different people, just saying that we are all unique, and that every things can be then correlated with what you eat or what you are doing in the day. Okay, I think I will just need to go a little bit faster. We have a lot of things to say. Now, completely going into another direction now on the cardiovascular diseases. That this is really then a really big issue in that there is a lot of deaths exactly on cardiovascular diseases. And we have on the plasma analysis, we have the lipoprotein subclasses analysis, and these support the research in a different area, like diabetes, like stroke, like atherosclerosis or cerebrovascular diseases, cancer, inflammatory disease, Alzheimer, and so on. That this is not only for one application, but really then for different research area. And now it's just more into details about what exactly, which kind of information you get. And that you get a lot of information about the main lipoprotein, like the triglyceride, the cholesterol, and that's everything you get when you are going to your doctor and taking them blood. And it's really that the general checkup, you get that. And then on top you get a lot of particles number and subtraction, which are really then important when you want to evaluate the risk of a cardiovascular event. And here is just one example on why it is important to look at this subtraction. Normally, the subtraction analysis is only done with a standard method, which is called the ultracentrifugation, and this takes really then long. It's not standard, and it's taken about 3 to 5 days to get the result. I mean that if you are not feeling good and you need to wait 3 or 4 days to know that you will have a stroke, then this is really something which is not good. And here what we see is this is normally what your medical doctor is looking, that it's looking at the main fraction, and he is looking at that, the LDL, the low density lipoprotein, are correlated with cardiovascular events. And if you are looking at that, or if the medical doctor is looking at that, means this is pretty fine, you are in the normal range, nothing to do. The same for the free cholesterol. And now, if you are just looking at the subtraction, then you see the effects that the 3 first subtraction are decreased, and the 4, 5, 6 increase. And this is like a B effect, and this is well known and well published and really used routinely, that this constellation really is an increased risk for cardiovascular event or stroke. And this is with the NMR and with the beta ELISA, you get this information within 10 minutes. And this is a real example of a patient. And 3 days after the analysis, he got a stroke. And this was really impressive to see that indeed, if you see that, mean that the patient do not really can feel great. And then on the same spectra, you can then get the information of small molecules, which are more amino acids or sugars and so on. And this is normally for just taking the example of the amino acid, this is normally something which is then difficult to get within one method conventionally. And with NMR, we can then get directly everything, because we are not doing any separation of the samples. We try all the time to measure that the samples as native as possible. And then, of course, then combining the lipoprotein information and the small molecules metabolites, you get more insight into the disease. And here is just one example is that you can look at the lipoprotein and on the same time look at TMAO, which for the plasma, if this is elevated, then this is associated again with the increased risk of cardiovascular event. That you can then really combine both the lipoprotein and the small molecules in one. I will just skip it. We have done a big wing test. We had 5 institutions, 11,600 or almost under platform. And we went real samples, and the results were really great, saying that the method is reproducible even if Luca is not present on that. And it is really great if you want to have a look at the publication. What I want to just here to illustrate is that there is a lot of publication using this lipoprotein analysis and saying that the parameter are really then great for the clinical routines. And the same for cancer research. Now, looking now at the urine analysis, we can then use that for, again, different research areas, which could be then, again, diabetes, kidney, cancer, epidemiology, biobank, or diet, which we have already seen, or even also metabolism. And this is really a dedicated area. And here is just an example about how it looks like, the report generation. Here and the information that it is done always done in different categories, and then you get always the concentration in millimole per mole creatinine. And this is then really important when you are just getting spot urine and not 24 hours urine, and you want to compare the urine between each other, and then you need to do that in relation to the creatinine, because creatinine is a marker of if you are then doing a lot or not. If you are then using the creatinine, and you can then compare everything else. And then you get some information about the LODs, and then it is then possible to compare the concentration with a reference cohort, which we measured to give you information if the metabolite is elevated or if it is in normal range. And then you get the information if you want. If you are more an NMR expert, you would like to see if the algorithm is working properly, and for that, then you see then the fit, and you can then directly then judge if the fit is good, and it means that you can trust the value, or if you need to look again into the NMR data. The NMR application with the Google quantification has really a high value in the inborn errors of metabolism area, because here in this case it is you need to have a lot of different and standard analytical methods in order then to be able to make a diagnostic. And like I could then show you already, in that we are then measuring the entire metabolic profile, in that we are not targeting and looking just at a dedicated metabolite, but we are looking at everything which contains a proton. And this allows really then to have insight on different metabolite categories, and then of course different involers of the patterns. And here it's just everything we are doing is always in order then to show that NMR is working. We are then participating in a lot of wind tests or a lot of proficiency testing, mean that we are comparing the NMR message with the standard message which are existing then in normal diagnostic lab. And this is just to show you that really that we NMR has not that great, and it's comparing then the NMR with other methods, and what you can see is that generally NMR is really great on the precision, linearity, and recovery. And then of course we can then help people to filter the information coming from the NMR, and this is an interface which is on the internet, and then it's ranking the potential invulnerabilities of metabolism, which could be with dedicated samples. And here we have a dedicated 12-hour sequence. And this is just an example on how it looks like when you have the samples with the invulnerabilities of metabolism, that the concentration of different biomarkers are relatively high in some cases. And here it's just comparing with the basic cohort, and then you have in black you have the actual samples, and visually you can directly see that some peaks are elevated and not normally in a basic cohort, and then we can then see that and this is then how it's working. You have the reports, and then you see directly that the concentration are elevated, but just by looking at the concentration. And then you can use the interface and to then rank and filter the information, and everything which is red means that it is related to an invulnerability of metabolism, and then it will then give you a link of possible invulnerabilities of metabolism. And then the medical doctor can decide, or you can decide if it's fit with the clinical information or not. And now just to finish, some word about the usage of the ICGEB platform on the biobanks, and why we are thinking that the ICGEB platform can help. Biobanks at the moment are not really that standardized. The need of the quality control of the incoming sample is really very important. And this is not the case, because you can really do quality control of each sample, and you can check different parameters, which check the different quality control parameters, is that really the body fluid you would like to have, or the people are saying it is, and you would like to know if there is any contamination, if there is any medication with the patient. We would like to see if it is then suitable for further study, and what you can get on top is really all these clinical biomarker identification. Like I said, we have the lipoprotein and we have the quantification of small molecules. This information can be then stored exactly then with the spectra and with the samples in the biobank. And at the end, we will not need to measure any samples anymore. But if you are then working with NMR institution, then you can just give or sell the NMR spectra or the result of the analysis. And this is just what it is possible to check with NMR. And this is just an example of medication. And this is really that paracetamol is a lot of the concentration of paracetamol in one patient is really that. And yeah, like I said, so that's the idea would be then to use then the spectra instead of use then samples. And I will then skip that due to the time, but you can really then use the spectra and do the target analysis, and it is really then important by treatment monitoring. You can really then check if a treatment is working and directly directly then act and change the medication for the different medication. And of course, you can make metabolic trajectory, mean that an assessment for the different medication, and this is then the different cohorts. We have a continuum, we have a cohort for newborn, and we have a healthy adults cohort, where you see that your metabolic profile is changing over the year, and this is then clear. And then now with the new NMR sample and spectra, you can really check if the age of the urine samples is referring to the correct age or not. And I will skip this. I will skip, and just like to let you know that with NMR there is a lot of research on long COVID, and the results are looking promising. But you can see really that people on long COVID are really not, or a lot of metabolites are still elevated. And as I hope that, so the background noise, but I hope that you could still then follow and understand. But it's really that the NMR is really robust, reproducible, that you can then use the spectra for further analysis. You can then get a lot of enabling tools which give you then some more insights about the foods. And of course, there is a lot of application in human body foods. Let's if you have some questions.
I would like to thank Ms. Cannet for making time from her schedule to join us today. So, after being in a different time zone from India, so we are open for questions, if any.
Yeah,
Next up we have Professor Neeraj Sinha from Center for Biomedical Research, Lucknow. So, Dr. Sinha has done his PhD in physics from Indian Institute of Sciences, Bangalore, and his postdoctorate at Department of Chemistry, Iowa State University, US. He has done his second postdoc at University of California, San Diego, USA. Today, Dr. Sinha will talk about applications of solid-state NMR in biomarker discovery. So, Dr. Sinha.
Today I'll talk about NMR spectroscopy of a bone cartilage tissue. You must have heard many different talks by different speakers, and in all those talks, most of the time the sample was in solution state. Whether it's a body fluid, whether it's a protein, or whether it's a nucleic acid. But the sample was in solution state. And today I'm going to talk about when the samples is in solid state. So can we do NMR? Answer is yes. But then there are different complications, there are different disadvantages, and also there are certain advantages also. So we'll see all the aspects of when we do NMR of solid system, what do we get, and how to get important information from those systems. And most of those solid systems are from the human body, whether it's a bone, cartilage, or tissue, and how it is, we can record that, and how we can make use of those systems. So feel free to interrupt me if you don't understand anything. I have tried to make this as a very general talk, and you can stop me anytime, you can ask me questions if you don't understand anything. So first let me just give you a brief introduction to what is NMR and what happens when the sample goes into the solid state. And I'll also talk about HR mass, which is for the soft tissue. So in solid also there can be some solid which are semi-solid, and some can be very hard solid like bones and cartilage. Cartilage is again a bit of soft tissue, but it has a lot of rigid part also. So this is something which you must have seen right from the first day of your workshop, that NMR is basically a phenomena of nuclear spins. So most of the nuclei in the periodic table have one peculiar property which is called as the nuclear spin. And it can be integer value or it can be half integer value. So for a spin half nuclei, there are many such nuclei. When you put them in the magnetic field, and if you don't have a magnetic field, then the energy associated with those nuclear spins are same. There is only one level. As soon as you put it inside the magnetic field of a spin half nuclei, you get variation in the spin energy level. And these are associated with value of spin minus half or plus half. And this difference between these two levels are very well defined. It depends upon the gamma. Gamma is the property of that nuclei, and V naught is the magnetic field. So higher the magnetic field, you have higher the separation. If magnetic field is lower, then it is lower the separation. But the separation also depends upon gamma, which is a particular property of that particular nuclei. So if the gamma value of two different nuclei are different, then in the same magnetic field, their energy level separation will be different. So gamma for hydrogen is very different from gamma for carbon-13. That is why in the same magnetic field, the carbon-13 For a typical value of gamma, so of a magnetic field like 11.7 Tesla, in the same magnetic field variations, the resonance frequency, which corresponds to the energy level separation, is about 500 megahertz for a hydrogen nuclei, but for the carbon, it is 125 megahertz. Why is it so? Although magnetic field is same, it is because the gamma are different. Okay. So, and then the moment you can apply energy on this system, which is matching with the magnetic field variations, energy level separation, you can cause a resonance condition. So this is the equation for resonance condition. Well, this is some of the picture of NMR spectrometer. You must have seen that, and this is the NMR spectrometer available in Lucknow. So you have one 800 megahertz. This is the part which generates the magnetic field. You have already seen that here in ICGEB also. And this is the part of the 600 megahertz solid state NMR spectrometer. So in solid system also you have the same thing as magnet, but then there are many different accessories which are associated with the system which we are working on in the solid state. And this is something which I will try to explain in my coming lecture. Well, magnet can be very big also, and it keeps on evolving also. So this is one of the magnet in the University of California at San Diego, where I did my postdoc. And during my postdoc, the 900 megahertz solid state NMR spectrometer used to weigh like this, where you have to climb all the way up to top to reach there, and then put the sample from behind. And as the technology evolved around 2013, they got 900 megahertz, which is replacing from here, where the magnet size is very small compared to that. So it is the same magnetic field, but at two different times. So this shows that the technology keeps on evolving all the time, and then you keep on getting a smaller and smaller magnet, but the field is same. Now the latest development says that how much is the highest magnetic field NMR spectrometer in the world. किसी को पता है? 1.2 gigahertz, which has been installed in Italy. Okay. So, and also there are few more which is coming up, and one is in Florida also, 1.2 gigahertz. So 1.2 gigahertz means the magnetic field in those magnets are so high that hydrogen nuclei resonate at 1.2 gigahertz. So 900 to 1.2 gigahertz means 1200 megahertz. So you understand the difference between megahertz and gigahertz. So giga means it's 1000. So 1200 megahertz is 1.2 gigahertz. So the field keeps on improving over the years as the technology is improving. Well, because of all these things, the NMR has a very wide variety of applications. Whether you are talking about chemistry, molecules, where you synthesize a new molecule and want to understand the structure, NMR has an application. You are doing some biology of a protein, nucleic acid interactions, or any such kind of interactions. There also NMR is there. Material science, where you have geolites or those kind of porous material. You can also do NMR spectroscopy to understand those systems. Medical science, where the MRI machine is entirely based on NMR concept, but in a slightly different way. There, in NMR spectroscopy, your purpose is used to NMR phenomena for getting the spectrum, but here the purpose is to use it to image the body part of that. And this is again the same concept, but for the imaging purpose. And I'm sure the earlier Professor Jagannathan gave a very good lecture on this. It also has a lot of application in petroleum industry. So let's see how this NMR signal is being generated in the NMR spectrometer. So I'll try to give one very simple picture, like how the NMR signals are generated in the NMR spectrometer based on some concept of spin and basic fundamental physics into that. So we know that certain nuclei has a property which is called as gamma. nuclear magnetic moment, and because of this nuclear magnetic moment, they have the nuclear spin has a magnetic moment mu, which is given as gamma I time h cross. H cross is the Planck constant, and this gamma, this I, which is the property of that nuclei, depends upon how many neutron protons are there in the nuclei. What is its atomic mass or atomic number? If atomic mass is odd and atomic number is even or odd, then the spin quantum number is half, 3/2 or fraction of that. If both are even, then the spin quantum numbers are 0. If one is even, other one is odd, it is 1, 2, 3 or integer values. So just as an exercise, you can try to calculate what is the value of carbon 12, carbon 13, proton, deuterium, and N14 based on these relations. So that will tell you like how the spin comes into the picture, because it is the property of that particular nuclei. Well, as soon as you put in the magnetic field, because of this magnetic moment associated with those nuclei, they are either processing is along the magnetic field or in the opposite direction of the magnetic field. And this precessional frequency depends upon how strong is the magnetic field and what is the value of applying magnetic field. So mu omega is the frequency of this precession, which depends upon the gamma times v naught. And if you can apply suitable RF matching with this energy level difference, you can shift from here to here. So this omega is gamma times v naught, which is this is the frequency and this is the frequency in hertz, like nu by 2 pi. You just divide by 2 pi. And gamma is the gyromagnetic ratio, or v naught is the external magnetic field. So spin half nuclei can have two orientation, either parallel or anti-parallel to the magnetic field. So for simplicity, we can associate this orientation as plus half along this axis and this orientation as minus half along this axis. But whenever we put a particular nuclei, we don't put a single nuclei, we always have a sample which has lots of nuclei. For example, like if you have prepared a solution of methanol or any other compound, you have 400 microliter, but then there are lots of nuclei into that. And each one will have its own magnetic moment, which will experience the magnetic field. So you will not have only one nuclei, but you have a collection of all the nuclei. So whatever nuclei that you see will have a random orientation of those magnetic moment in absence of magnetic field. But the moment you put the magnetic field of all those nuclei, they will be either parallel or anti-parallel into that. So this is the kind of situation happens when you have external magnetic field. Now, now how many nuclei will be in the positive state and how many nuclei will be the anti-parallel state? What will how will we on what factor will it depends upon how many nuclei are in the positive state or how many nuclei are in the anti-parallel state. So what factor will decide that? Yes, of course, it will be decided by the strength of the magnetic field, because the strength of the magnetic field says that how much energy is associated with the positive one and how much energy is associated with the negative for a one particular nuclei. What I am asking is that if you have lots of samples, lots of molecules, so each one have a different kinds of nuclei. Okay, so there will be certain nuclei which will be in the along the magnetic field, certain will be in the opposite of the magnetic field. So what will be the ratio of those fractions and on what factor will it depend? Okay, Gamma is anyway is important because gamma is associated with how much is the energy separation. But like suppose you have 10 to the power 23 nuclei, there will be some fraction which will be up, some fraction will be in down. So what does those fraction depends upon? it will depend upon the temperature, because not all those molecules are in the 0 degree Kelvin, where all the energy level separation, they are also moving, and there is a temperature associated with that. So it will depend upon the temperature. Higher the temperature, there will be very less fraction, which is difference between the two. But if you can go to the lower temperature, then there will be a very large separation between the two energies. So this is the Boltzmann distribution, which you have studied in the physical chemistry class. Okay, so the number of nuclei in the positive state or negative state will depend upon how much is the temperature of the sample. If you increase the temperature, the difference will be more. Well, in NMR's spectroscopy, we try to simplify things in order to explain how things are working. So, what I did was, I draw a XYZ coordinate system. Well, I can always do assign one particular direction as x-axis, other direction as y-axis, and third direction as z-axis. And for simplicity, we have done in such a way that z is the direction where we have the magnetic field. Okay. So when you have many nuclei, each one will be either processing here or processing there. But since the energy associated with this one is lower, because it's the direction of the magnetic field, there will be slightly higher number of nuclei along this axis compared to this axis. This is something which everybody agrees. Correct? So if you try to make a sum of all those magnetic moments, so this will be the magnetic moment of the entire sample which you have put inside your magnetic field. Then there will be a small fraction which will be along z-axis. This is something which everybody agrees. So if you take a sum of all those vectors and then calculate what is the total magnetic moment of that sample, where there are 10 to the power 23 nuclei, then it will be along z-axis. Is this something which everybody agrees? Okay, why is z-axis? Because z is the direction of the magnetic field. This is the direction which we have chosen as the magnetic field. So if we have one nuclei, then it can be either parallel or anti-parallel. But if you have a large sample of nuclei in a magnetic field at a particular temperature, then there will be a net magnetic moment, net magnetization vector, which is around the z-axis. Okay, so we will talk about all the description in terms of this net magnetic vector. Why? Because we don't have one nuclei, we have a collection of nuclei, and this is the net magnetic moment which all those nuclei produces when placed in a magnetic field. And of course, if we talk about net magnetic moment, then again the net magnetic moment can also be flipped based on the energy level separation. So now we are talking about the energy level separation of not just one nuclei, but all the collection of nuclei. Because this collection of net magnetic moment comes from the sum of all those collections. And then we can apply a suitable RF and then calculate how much is the energy it is going to absorb and go from here. Now comes the picture like how the NMR signals are being generated. So you see, when you have a magnetic field and collection of nuclei, the net magnetic moment is around z-axis, and z-axis is the direction where we have the magnetic field. Okay. Now, if you have a coil where you are putting a radio frequency, and this radio frequency is such that it is matching with the resonance frequency, then as soon as you switch on, and suppose this is along the x-axis, okay, so when the RF was off, all the magnetic moment from the sample was along the axis. The moment you switch on this RF, all these nuclei will see not only the external magnetic field but also this RF, which will also produce a magnetic field. So the net magnetic field will be along x-axis. So because of this along x-axis, the magnetic moment of the sample which was along z-axis, it will try to change, because now when you switch on the RF, it is not just seeing the external magnetic field, but it is seeing this also. And the magnetic moment is not along this axis, so it will try to persist along this x-axis. And because of this precision, precision, its position will change. Now suppose if I switch on the RF for a very short time, then it will shift by very short angle. If I increase my time, then again it will change for a longer time. Now suppose if I have switched on it for such a time, such that it comes from here to here. Okay, so for how much angle did I allow the magnetic moment to shift? 90 degree from z axis to y axis. How did I do it? By putting an RF which has a frequency matching with the resonance frequency, and then allowed it to go from here to here. So this is called as 90 degree X-pulse in the NMR language. Okay, and if we apply the RF along y-axis, what will happen? Suppose instead of x-axis, my coil was along this axis and the magnetic moment was this axis, and then it will flip to x-axis. So again, it depends upon how we are applying the RF and for how much time we are applying the RF. So it will change the magnetization from z-axis to this axis. Now what I did another part, like I just left it along y-axis and switched off the RF. What will happen? Well, the external magnetic field is something which was already there. Okay, so all these magnetic moment which is coming from the sum of all those magnetic moment of the nuclei, now it will not see RF because RF has gone. I switched on that. It will see only the magnetic field. So the magnetic field is not along m0 axis, but it is perpendicular to that. So since it is perpendicular to that, it will try to go back along z axis, but it will also try to persist along this axis because it is perpendicular to that. So the force will depend upon how the relative angle between the two are there. So it will try to persist and try to go back along z axis. This is something which everybody agrees? No, you don't agree. Okay, yeah, tell me. Yes. Yes. So the magnetic field is along z axis. The force is along. The magnetic moment is along this axis. But since it is perpendicular to that, it will not go directly from here to here, but it will go by persisting along this axis. So you see, it will keep on persisting along the xy plane, and then it will try to go back because it is at a perpendicular axis to that. Okay. So it will ultimately, if you wait for a very long time, it will go back to the z-axis. Why z-axis? Because that is the direction of the magnetic field, and then all nuclei will try to align with that. But during the precision process, it will be persisting in the xy plane. Okay. Now what I did was, in the xy plane, I have put a coil here. And this is the same coil for which I have applied the RF. Now when I switched off the RF, the coil was still there. Okay, so this persisting magnetic moment from all the nuclei will produce a field at the site of this nuclei. Again, this is a Faraday law. Like if the magnet is persisting, it will produce a current at the site of the where the magnetic field is being generated. So this coil will now pick up a signal of frequency, which is the precisional frequency of those magnetization. Okay, and this precisional frequency is being picked up by this coil, which is called as receiver coil, and then converted into the amplified electrical signal, and then recorded in the NMR computer. Okay, so now if you see here, as soon as it is along x-axis, so since it was very far, so it is started from one value. As soon as it comes along the x-axis, it will be 0, and when it goes back here, it will be again like this. So if this coil was along y-axis, it will start from 0 because the magnetic moment was along the y-axis, and then it will pick up positive, negative, and oscillate and try to go back to 0. If you go for a very long time, then again all the magnetization has gone to z-axis, then this coil will not pick up any signal because there is no change in the magnetic moment produced by those nuclei. Okay? So, in principle, this signal which is being picked by the coil will decay. How fast it will decay? It will depend upon how fast the magnetization is going around the z-axis. What will be the frequency of this signal? It will depend upon how fast the nuclei is, magnetic moment is precessing. So if we can figure out what is the frequency by doing a mathematical transformation which is called as Fourier transform, this will give a frequency, and this frequency will be equal to the precessional frequency of all those nuclei where the sample was placed inside the magnetic field. So that is how you get the NMR signal. Clear? If the nuclei is precessing at a very different frequency, you will get a different kind of these signal, and then of course the NMR spectrum will be different. If in your sample there are different types of nuclei having slightly different electronic environment, they all will possess a slightly different frequency, and then if you record all those spectra and measure the frequency, the signal will have all those frequencies present into that. So you will get all those signatures coming from the NMR spectra. For example, like if you have this kind of system, this magnet nuclei will experience a slightly different magnetic field because of electronic environment compared to this one and this one. That is why their frequencies are different, and then you get a different kinds of line. Is it clear? Okay. Now in NMR spectra, how do we plot that? You see here I am putting it like this is 1 ppm, 2 ppm, 3 ppm, 4 ppm. In terms of frequency, it is the same. Increasing ppm is increasing frequency. So which one has the largest frequency? This one. And this one has the smallest frequency. Okay. So that explains how the NMR signals are being generated. Well, if you have a complicated molecule, menthol, or different conformation of this menthol, then all these nuclei, when it is placed in a magnetic field, will have a slightly different electronic environment, and that will produce a slightly different magnetic field at the site of those nuclei. And if you have a collection of that, then they will have a slightly different frequency, and all those frequencies will manifest in the signal picked up by that coil. And when you amplify those signals, do the Fourier transform, you can actually figure out what are the precessional frequency of all those nuclei. And if it is associated with different conformation, you can detect it. So this is the basic idea of NMR spectroscopy. Well, there is another very important concept of NMR spectroscopy, which is called as two-dimensional NMR spectroscopy. I'll try to explain in a simplified way what is two-dimensional NMR spectroscopy, carrying out the concept which I explained earlier. So, you know that in two-dimensional NMR, nothing is in two-dimensional, it is just the data we are collecting into it. And you know how the NMR signals are being generated. It is the nuclei which has been perturbed from z-axis to x-axis, and then its precision is there, and you are picking up those precision by placing a coil suitably and amplifying those signals into that. So in two-dimensional NMR, there are different ways of recording the NMR. First part is called as preparation, then evolution, then mixing, then detection. So in an NMR like that, this is the time axis. Okay? And D1 is something, some delay which I have given, did not do anything to the nuclei. They are peacefully sitting there, and their magnetic moment will be along z-axis, where we have the magnetic field. So D1 is the time into that. Then as soon as we start this preparation period, we apply a pulse. This pulse has the same frequency, which is the resonance frequency of the nuclei which we are trying to detect, and its time is in such a way that it just flips the magnetization by 90. Then again we did not do anything. So since we have switched off the RF, the nuclei will try to persist, produce a signal at the site of that nuclei, and then depending upon how much time we have given, it will persist and its position of magnetization will change. After a certain time you have put another pulse. So wherever those magnetization was there, they will experience this RF. So the effective field will again depend upon how much is the direction of this RF and how much is the time. And during this time again it will persist, and then you switch on your RF. Then you switch on your receiver. So you start acquiring the signal. So wherever the magnetization was there, after doing all these things, it will try to go back along Z axis by doing its precision. And again this precision will depend upon what are the different nuclei and what are the different interactions, and you start acquiring there. But in case of 2D NMR, you don't acquire just one signal, you acquire a series of signals. So what you do is that in this evolution period, you keep on changing. In the first experiment, you had an evolution period for a very short time. Systematically, you increase it by some more number, and then some more number, and you keep on acquiring all these data. So this data at this particular point will have all the precision frequency, but if you keep on changing this time by systematically by a small amount, you will get information about what is happening in this also by looking at this data collection collectively. Okay, so that is the idea of two-dimensional NMR. You get this series of signal which was collected at this particular time, and you plot it in such a way that during all these FID, I'm calling it FID, free induction decay. This is just a name, free induction decay. Because why free? Because there is only magnetic field. Why induction? Because the free processing of magnetization produces induction at the coil. Why decay? Because ultimately it goes to the Z-axis. So I'm calling it free induction decay, FID. So these FID are collection of data. But if we compare one by other, there is a slight variation in terms of mixing. Evolution. Okay. Now if you do a Fourier transform of all these things, in first case you will get some signal, in second case you will get some other signal, in third case you will get some other signal, in fourth case you will get some other signal. But all these signals will not be the same. Why? Because my evolution period was slightly different. Okay. So this signal, suppose it is both peaks are positive, in this signal it will be negative also. Because this particular magnetization has persisted in a slightly different way using the evolution period, and there is a difference between the two evolution. Now what we did another trick, like we just did a Fourier transform along this axis also. Okay. So for example, like then it will tell us like what is the persistent frequency of these nuclei during the evolution period. Because in each of the FID, my evolution period was different. The spins were evolving in the evolution period. So if they are evolving with some particular frequency, that will manifest by doing a Fourier transform along this axis. So we will get a two-dimensional contour plot where the peaks are slightly different. So this is how two-dimensional NMR is being generated. And there are a variety of two-dimensional NMR. Each one has the same basic concept, but with a different evolution period and excitation. Well, you must have heard about names like Rosita, Toxie, and head-core experiment. So they are all being generated in such a way that different nuclei are put up with the different combinations, and then you get different kind of information from the system. For example, like COSI, where you get one bond correlation experiment. So you have this kind of molecule and each peak are assigned here. But if you want to have information like which one are coupled with each other, then the COSI is a very good experiment. because it can give one close connectivity through Jacob. Toxi, when you are talking about the downward correlation, then all these map can be interpreted in terms of those molecular structure into that. Head core is one such experiment where you have a carbon spectrum on this side and hydrogen spectrum on this side. You want to figure out which are the carbon associated with which hydrogen. Then head core is a two-dimensional experiment where you can, by looking at the peak position, you can figure out which are the carbon having a different proton associated with them. Why the carbon and protons are different resonance frequency? Gamma are different, okay? But they are in the same. So if carbon spectrum has many peaks, hydrogen spectrum has many peaks, and you want to figure out which are the carbon resonance associated with which hydrogen, then head core is the two-dimensional experiment in Newton. Well, so far so good. You get a beautiful spectrum of solution state NMR, you can get 2D. But what happens when you have the sample in the solid state? So this is just one such example of solid state spectrum of glycine. Carbon-13 spectrum of glycine. So you see you get a spectrum like this. It is very broad. Why broad? Because glycine is in the solid state, so all those nuclei which you have put inside the magnetic field, they are in solid state. So they will experience the magnetic field in the solid state. So in the solid state, the electronic environment is also in solid state. So each nuclei will have a different orientation also, and these orientation are not changing with respect to time because it's in solid. But in solution, there will be a random Brownian motion because of which the orientation keeps on changing as a function of time. But in solid, everything is rigid. So each nuclei will experience the field depending upon how it is oriented as well as how is the electronic environment. And because of this problem, you get a broad spectrum. Okay? So this is the carbonyl part of glycine, and this is the carbon alpha, C alpha part of the glycine. So you get a broad peak. But this broad peak also has an information like how the electronic environment are changing. And there are ways by which we can simplify this spectra, which is called as Malik angle spinning. And then based on those Malik angle spinning, even though the sample is in the solid state, you can get sharp line like this. So this is the solid spectra of glycine when the sample was in solid state, but we have applied some solid state tricks, which I will explain, and then you get a sharp line into that. So this can be more useful into that. In solid protein also, you can do Malik angle spinning to get characteristic feature of those NMR spectrum, and then you can get line which are associated with the side chain, aromatic backbone, alpha aliphatic part, and methyl protein. And if you record the human blood serum sample, you can get all those molecules, you can assign them. So the blood serum is a biological fluid where the molecules have been assigned to citrate, lactate, all those. And human urine sample can also be NMR spectra recorded, as shown in the earlier presentation also. So if you record an NMR spectra of urine of a healthy individual, you can assign many of the B. If there is some renal damage, then of course NMR spectra will be different because it has information about the molecule which is associated with the renal damage, and then we can assign changes happening to get information about what happened during the renal damage. So how do we get good lines from the solid state NMR spectrum is how we do the NMR spectroscopy also. So this is called as high resolution Malik angle spinning of soft tissue. So this is the NMR code of HR mass. So you put your sample inside this part where there are coils around this thing. So x-axis coil which apply the signal and picks the signal from that is around this axis, is inside this. And then your sample is being put in a small tube around this axis. So, and everything is inside the magnet. So you see magnetic field is direction is this, and then the sample goes here. And this sample is not just static, but it keeps on rotating at a particular angle. And this angle is called as magic angle. And the way we do the magic angle spinning is, the sample is inside this rotor, and then we put high pressure air inside this, so that it floats in the air. And then based on the another air pressure which is being given at the top of those rotor, the sample spins. So the sample keeps on spinning when I am recording the NMR spectrum. That is the tricks for simplifying the NMR spectrum. So the sample is still in the solid state, but its physical condition keeps on changing as a function of time. So different types of tissue, whether it's related with XDC, gallbladder cancer, and chronic cholecystitis, can be studied by those NMR spectra. And there are certain things associated with making those samples and then putting inside the NMR rotor. And those rotors are very special kind of rotor, where you put your sample, tissue sample can be big also and can be small also, and we put them, rinse them in D2O water, and then it is being placed inside this, whether at the top or the bottom, depending upon the size of the tissue which we have, and everything is put inside that NMR probe, where it is spinning also while we are recording the NMR spectrum. If you don't spin, then everything is solid, so you get a drop line. Well, this is some application. Mouse liver tissue sample. If we just do HRMS, high resolution manual spinning, you get sharp lines, and all these lines can be assigned to different molecules present to that. And for the same sample, if you want to do some lipid extraction or aqueous extraction and do a solution state NMR, you can also get a good deal of information from the lipid part and the aqueous part of those samples. But here no extraction was done, everything was in a native state, just dipped into that, and then we are recording that. So this has a certain advantage because we are not modifying the tissue sample and getting information of all the components present inside the tissue. But when we do extraction, we change the sample. No powdering, just a small piece of the sample put inside dipped inside that, because it's a tissue sample. And then everything is being put here. Of course, with the spacer, since you are spinning, you need to make sure that the sample is homogeneous, otherwise it will not spin. So, yeah, so it has a lot of advantage of linear tissues. You can do two-dimensional NMR also on this tissue sample to get connectivity and confirming the assignment. Well, parental dry mouse multiform tissue sample has been studied by HR mouse, and no changes have been assigned, including the 2D HSQC or different regions of the healthy and highest degree of necrosis of restricted bacteria, glioblastoma, multiform disease condition of it, and we could get the metabolic alteration of those tissue sample, which is giving the information about directly coming from those tissue samples. Different types of tissues give different types of HRMS spectrum, whether we are talking about red blood cell, hippocampus is the region of the brain. Sometimes in brain surgery you can remove some tissue from the brain, then do HRMS, figure out what is happening there. Liver tissues, renal cortex, and so all these things gives information about the state of those tissues, what are the different molecules by doing NMR spectroscopy. And we have to do, of course, magnetic. there are ways by which we can do in vivo MRS. Suppose you are looking at this particular region of soft tissue, you get MRS signal combining with MRI, like choline, creatinine, citrate, and if you do the same tissue HR mass, you get much sharper line and many more molecules coming from there. Of course, these molecules, choline, creatinine, and citrate are there, but here you get a very broad line because it's like MRI spectrum calculated. But here you get a much sharp line and many more molecules can be assigned. So this is the advantage of doing this. In last I will talk about bones. Bones are even harder tissues and more difficult to study, but it can be done by magic angle spinning and a lot of other components into that. So there are ways by which you can get information about the bone. And bone is basically a hierarchical material where if you look at, if you try to zoom it at this part, you have osteum and Hermitian canals. And then if you go even deeper in the 50 micrometer in, then there are fiber patterns. And these fiber patterns can be zoomed to 5 micron and 500 nanometer, where there are collagen molecules, collagen fiber, and inorganic minerals are there into that. So bone has three main components: inorganic minerals, organic protein, and water molecules. Okay, and the intricate interactions between all these molecules are important to understand the bone physiology and bone understanding. And this can be done by NMR spectroscopy, because NMR spectroscopy can study the intact bone. So we take a portion of the bone, put inside the NMR meter, and then we got the NMR spectrum without doing any harm to the bone sample. Of course, bone has been removed from the animal, so already there is a harm, but we are not doing any processing to the bone sample. Well, why do we want to study bones? Because the bone as a function of time changes, and as you can see, the young adults' bones are very different from this, and osteoporosis is one such major problem associated with bone, where bone becomes susceptible to fracture, but recovery is very fast. Recovery of bone in children are very fast compared to older people. So we can look into what are the changes which happens as a function of time when the bone becomes weak. So one such experiment which we did was like trying to measure what is the where is the water inside the bone matrix by looking at collagen protein and hydroxyapatite crystals, and then we can look at the carbon spectrum, which will give the spectrum of the collagen protein inside the bone matrix. And then we try to figure out how much distance it is from the mineral part by doing some solid state NMR experiment, which is called as the radar experiment. And there we can measure the distance between collagen and the mineral part, and then how it changes as a function of water content. We found that it changes as a function of water content. If we remove the water, then the distance between collagen and mineral part decreases. So that confirms that there is a water in between the collagen part into that. We can do many more advanced experiments to figure out how the collagen molecules are oriented inside the bone matrix, and whether the water is playing any role in the collagen protein by doing some two-dimensional NMR experiment. And these are NMR experiments are done on hydrated bone or HDHC bone, dehydrated, or collagen when it is completely extracted from there. So the pattern which we get is a true indication of collagen matrix for how it is arranged inside the bone matrix. And this was done for a bone sample which is kept at a magic field in the spirit, and then probing all those nuclei up to the. We can look at different types of water inside the bone matrix, whether there is a surface water, whether the water is inside the collagen and mineral interface, and how it is changing when we are applying the forces into the different types of bone. So this study let us water, and as soon as the bone, you apply a pressure or force into that, the water from free part goes to the collagen part, and as soon as the force are removed, it goes back into that. So we can look at this mechanistic kind of details also, where we get information about how the bone functions by looking at it. Cartilage is another important biological tissue. Cartilage is in between the bone part, which provides cushion to the bone movement. And again, we can scrap from the animals this cartilage. So these will be small pieces of cartilage put inside the rotor, and then do NMR spectroscopy of that to get information about the cartilage. So cartilage has a lot of different types of molecules. Collagen is there, water is there, and hyaluronic acid is there, chondrocytes are there, and all these molecules will give us a signal. GACs will resonate here. We can assign the collagen part into that. And we have done some sensitivity enhancement experiment for the cartilage molecule, where we can enhance the mobile component signal also and the rigid component signal also. Cartilage is a very heterogeneous molecule. Collagen is more rigid. There are certain inorganic minerals, then there is a water, and chondrocytes are very flexible molecules. So they all have a different heterogeneous motion. So based on these motion components, we can get their signal also. Many of these signals can be assigned to this GACs molecule, and how it is interacting with the collagen part is giving us information about how the cartilage structures are being arranged inside the molecule. So again, it's a native cartilage put inside the solid-state NMR rotor, and then the NMR spectroscopy. So in terms of NMR spectroscopy, it is available in tissue, bones, and cartilage. All these part of that can be studied by NMR. So whenever in an animal model there is some disease, there will be some changes which will be associated here and some like the other part. So NMR can give you the complete picture about the tissues and whether it's a soft tissue, hard tissue, and of course biological fluid. So with this, thank you everyone. I'll be happy to take questions if there are.
So first my question is that in your previous slide where you was like the 13C NMR. So how is it possible to do 13C NMR with the tissues and like bones?
Correct. So when you understand that we cannot do carbon 12 NMR, we can do 13C NMR. And 13C has a natural abundance of 1.1%. So whenever you do NMR, you have to enhance the signal of 13C. So in solid state, there are ways by which you can transfer polarization from proton to carbon 13, and those kind of experiments are called cross polarization, where you can enhance the signal of carbon 13 in a natural abundance by cross polarizing from proton to carbon. And those experiments were developed in 1970s, and now it has been routinely used in that. So I talked about magic angle experiment, but the other important aspect of solid state NMR is cross polarization with magic angle experiment. So those increases the signal that is.
So this thing is also possible in the solution NMR?
Of course, in solution also natural abundance carbon 13 NMR is being done routinely, but it takes some time. Okay, because cross polarization technique is not there, but there are inert based techniques which can enhance that.
And
Even the natural abundance N15 now people are doing for protein. Yes, we have done a lot of natural abundance N15 in the solid state. So it's you need to enhance the signal. You need to do a lot of signal.
And my second question is that how you prepared the samples for your solid state NMR?
Well, the picture says that here we put scrap out from here, small pieces put inside the NMR rotor, and here for the bone sample we have a such a way that it goes inside and then just put inside the
So,
NMR.
like direct, nothing, sample preparation, nothing. So you're just taking the sample and putting it in.
That is why it has advantages. You see, for study of bone, all these methods were available, but all these methods require sample preparation. For X-ray, you need a crystal. Of course, powder can be done, but then there are lots of things which has to be removed. Neutron, backscattering, wet chemical, FTIR, they all require your bone sample to be modified before you can apply those things. But solid state NMR is the only technique where you can just use that, and whatever is there available in the system, it will show up here.
And my last question is that how that magic angle is magical.
Yes, so that's a very good question. So, you see, all these things, NMR spectra is basically just the signature of all the interactions which a nucleus plays inside the magnetic field. Okay, so there are many such interactions which is called as the dipole-dipole interaction, chemical shift anisotropy interaction. And if you look carefully, those depends upon what is the angle between magnetic field and the nucleus. And it comes from this relationship. So you see here there is a spin part of that, and then there is a 3 cos square theta minus 1 part. And if you do some simple mathematics, 3 cos square theta minus 1 goes to 0 when theta is exactly 54.7. That is the method. So when you do the magic angle, you are putting all your NMR interactions with respect to magnetic field at a particular angle. So all these things get modified and your nucleus does not just see all those interactions but averages of that. So that is the magic.
Thank you.
Yes.
Hello, hello sir. Sir, in spectra, solid state spectra, you got broader peaks.
Right.
What
If
was
you don't do anything,
what
just
was,
record that.
my first question is, what is your reference? Like in solution state, we have a reference. Also in solution state, we lock our field, but in solid state, we don't lock.
Yeah.
So why, sir?
Yeah, so in solid we don't lock because we don't need lock. But because the lines are anyway broad, even with the best conditions, you get a broader line. So you don't have that much resolution because of system. That's why you don't need lock. But in HRMS, where you can still do a very angle spinning and very soft tissue, there you have a lock. Because you dip in ND2 and then you can do a lock and changing it. So it is because of the nature of the spectra. For variety of solid, you don't need lock. Because during the course of experiment, the magnetic field does not change drastically such that the spectra is shifted. Does that answer your question? And the second one about referencing. So referencing is generally done by internally. Like here, we know that the carbonyl peak resonated at this particular thing, so we can reference there. But if you are recording after 2-3 months when the magnet has shifted, then again you need to have referencing.
So the shimming will not be a problem.
Shimming we do a lot of without lock, and based on the NMR, looking at the NMR spectra. But again, shimming is, we don't need a very good shimming because our line widths are not that sharp. But sometimes what we do is that we put some D2 or to lock it and then do shimming and then remove that. So again, it depends upon the kind of spectra and the content requirement which you have.
Thank you, sir.
Okay, sir, why you tell that RBCs are solid? RBCs, red blood cells,
Because RBC also
with
has some solid
spinning,
problem.
it will hemolyze and end up in solution state.
Yeah, so it has a major part of serum is blood serum is solution, but then the cell itself is semi-solid.
But spinning will not affect the
structure of organism.
Okay, so you are asking like, are we spinning so fast that it is capturing the molecule?
Exactly.
Yeah, sometimes a tissue sample can be raptured if you are spinning
Monoids
30, 40 kilo. You have to
Specific.
make sure that for
Yeah.
those samples we need to spin at slow ice. Just for that amount of it. Bone, I can spin at 60 kilometers without affecting bone.
Okay, thank you.
I just wanted to know the principle of radar experiment. How it is
Radar
done.
experiment. Yes, I can discuss quite a lot about it, but radar is basically measuring the distance between two heteronuclei. So in solid state NMR, the two heteronuclei also has a dipolar coupling, and this dipolar coupling depends upon what is the distance between the two nuclei. Okay, and in magic angle spinning, you average out the dipolar coupling, but before it average out in one router period, you apply some pulses to reintroduce it. Okay, so while recording the NMR, you have removed it, but during the evolution period, you can reintroduce it. So by seeing the comparison between the two signals, you can get some estimate how much is the dipolar coupling. And then the dipolar coupling depends upon distance, you can get the So this is a very simple explanation, but there are very different ways to do it, and it's a very accurate way of measuring the distance between the two nuclei, even though the sample is very soluble, and it has a picometer resolution.
In the evolution time, you are giving the
Trying to reintroduce the
step and this.
dipolar.
Neeraj, two questions basically. So in bones, have you ever tried looking at the calcium particularly?
Yes, there are calcium has a very low sensitivity. People have looked at calcium. There are 2-3 papers, and calcium is in the mineral part, and there are advanced
Because calcium has a hydration cell, so the water structuring will,
the calcium.
so it will depend a lot, define the calcium signal also.
Calcium has a problem like it's a quadruple.
Yeah.
Very low sensitivity and all those.
But natural abundance is something like 0.15 or something.
Very low abundance.
Uh-huh.
And quadrupolar. So for quadrupolar nuclei, the solid state NMR is very different because of quadrupolar.
Yeah.
So I did not look into that, but Ramurthy has published.
And DN, I was thinking because in bones, you use the DNP to really enhance.
DNP calcium can be done, but we are collaborating with Florida and but right now they don't have a DNP for calcium.
Okay.
We are trying to get it. Then I think
And P31 also that?
P31 is a natural abundance is high.
I think almost 100%.
So there are at least 30-40 studies on P31. Different types of amorphous part is there, and then crystalline part is there. How much is the thickness into that? And very recently, one of our paper is being accepted. We looked at the dynamics of P31, mineral part, and how the hydration cells keeps on changing. So P31 is enormous.
And second part is when you do the soft tissue and other thing, that's the hemoiety, the paramagnetic part, creates another problem really, because you cannot.
If you are looking at proton, it will affect the relaxation part.
Yeah,
Of course.
it is shifted completely, broadening also, and that you cannot get over even by the magic angle.
Yes, but there are not a lot of tissues. Why do you think they are actually?
I know.
Iron,
Hemoiety.
but then it's not in the paramagnetic state to affect the iron. I think the oxidation state of
Yeah.
iron,
Yeah.
because it is, for soft tissue there are so many HRMS people. None of them talk about how the iron. See, I mean, the NMR spectra was.
Yes, if it is bound is perfectly Fe2 plus.
Yes.
But if it is some part is Fe3 plus, oxidation, then that's one thing, because you are taking out a tissue and it's prone to oxidation.
Correct.
If Fe3 plus is quite. Right. Thanks, Lindsay.
Thank you so much, sir. It was an amazingly informative talk. So now I would request Dr. Neil to elucidate. So we are breaking up for tea, and after 20-25 minutes, we'll be back again here for labs.
So today's program is a bit changed because one of the speakers could not come, Kavita, because of illness at home. So what we'll do after this thing, after the snacks, we'll go directly to the NMR room groups, and we'll do a titration with a protein which Priya has with the 80 adenine binding. I think that then you see the where it binds and plot the chemical plots and all this thing. And then we assemble here again at 4 o'clock, which is the key lecture with Professor K.V.R. Chari, who is director at ICER. And he is the one who started the protein NMR in India. He started the protein NMR. The first protein structure came from his lab. So it is a significant one. And then we will distribute certificate during the dinner, and there are some other things which so many other things will be given tomorrow. Okay, after the 2 talks tomorrow. Okay, so that's the plan.